Hey you HVACers, this is the HVACR apprentice, and this is a video walkthrough of a service call to replace a failed thermistor on a Mitsubishi City multi-heat pump system. I've already diagnosed this failure prior to the recording, but I tried to take the time to comprehensively document some processes that may help folks with their own interactions with this equipment. I'm by no means a ninja on this stuff, so if you can learn me a thing or two, please comment below. I'll be connecting to the MNet with my maintenance tool at TB3, which is located in the lower right of the main printed circuit board in the master outdoor unit. The maintenance tool attaches to the laptop using a USB A to B cable and to the MNet via alligator clips, which I always secure to the equipment with zip ties. If you have multiple devices attached to your computer, you will want to know which COM port your maintenance tool is attached to by viewing the system ports in your device manager. I gain access to the MNet by choosing MN converter in the maintenance tool software and identifying which model maintenance tool I have and which COM port it is attached to before clicking select. I use the auto search button to populate the address grid, which will display the equipment attached to this MNet. The equipment flashing red indicates a problem, green denotes operating equipment, and gray equipment is inactive. I click the Maintenance Data button and choose the master unit at address 51 associated with the equipment currently in error before clicking Monitor at the bottom of the window. The malfunction log shows repeated 1102 error codes at address 53. Next, I close the Maintenance Data window, click the Monitor button, choose the master unit at address 51, and click Confirm. In the window for the outdoor unit at address 53, I see that TH4, the discharge line temp thermistor, is currently 289.6 degrees Fahrenheit. I click Return to exit the status monitor and choose not to save the data collected while monitoring. I already know where the outdoor unit with address 53 is physically located, but if you weren't sure, you could reference the model number in the top window for that unit in the status monitor and match it to the nameplate of the physical unit. The address is also denoted on the main printed circuit board in each outdoor unit by the address dials, often labeled SWU1 and 2. I think it's worth pointing out that I'm not using an impact gun on these panel screws, mostly because they are machine screws and also because I'm not a lazy bastard. I'd like to use these moments to think through what I have left to accomplish, how I will manage to do it, and where I am with my time. TH4 reads discharge line temperature and is located between the compressor and the oil separator on the discharge line. This is a proprietary negative temperature coefficient thermistor with non-standard resistance values between 10 and 700 kiloohms, which lands on the printed circuit board on pins 3 and 4 of a green Molex connection, which is labeled CN211. You can't just slap a standard 10 kiloohm thermistor in these units, although I imagine in a pinch you could possibly wire in a 40 kiloohm resistor to make the printed circuit board think the discharge line was around 150 degrees. I haven't tried this, and it's also possible that the unit would never start seeing a running discharge temp before the compressor ever began to spin. Once I had the new thermistor installed, I found that I had to cycle power to all 3 of the outdoor units in this system. I'm not sure if this was necessary. I tried clearing the alarms in the maintenance log, but that didn't appear to be enough. Once the outdoor units were powered back up, I ran maintenance tool again, and when searching the addresses, found that all equipment was operational. After the address grid was populated, I went back into the status monitor by clicking the Monitor button, then selecting the master outdoor unit for this system at address 51 and clicking the Confirm button. What I want to do next is confirm that this system is operating well, and to do that I will be driving the system into full cool mode by performing a test run, which will activate all indoor units within the system. There is no great load in the building, but driving the system to full cooling will give me an idea of how it will be operating when there is a large heat load for it to remove. From the status monitor, I click Drive Operation and then IC. When the drive window appears, I want to choose Set Selected Addresses and check the boxes for On-Off, Mode, and Fan Speed, and set their values to Test Run, Cool, and High. Once the indoor unit addresses are selected, I will click Transmit, and after confirming, I will close the drive window. Once the system has been driven to test mode and I'm back in the status monitor, I will briefly click on the refrigerant circuit diagram, which displays the status monitor values for the system overlaid on a live piping diagram. This is a good way to get your head wrapped around how the refrigerant flows in these systems, and also gives you a visual representation of the data from the status monitor windows. The status monitor has now been running for 22 minutes. The data are updated every minute, and you can scroll through these minute-to-minute values by using the play, forward, and reverse buttons in the upper right-hand corner of the screen. I've highlighted a handful of values that I wanted to keep track of by clicking on them individually. If you're wondering what these values represent, you can click on their title above the value and a small window will pop up explaining what they are. For instance, if you clicked on TH4, the window would pop up and tell you that it is a thermistor reading the discharge line temperature. One thing in particular that I'm looking for are superheat values for the indoor coils between 0 and 10 degrees. I'll do another video in the future on what many of these values should be and how to interpret them if they aren't. Now I go back to drive operation, choose IC, and reset the system to normal operation, transmit the command, and close the drive window. Now that I'm finished, I will click return, and it will give me the option to save these 20-some minutes of data in a file on my computer. I could open this file later with the maintenance tool software by choosing offline mode instead of MN converter when the application opens. In conclusion, I tried to condense this video as much as possible. Working on VRF equipment is anything but fast. Most of the computer work you've seen here takes tens of minutes at every turn. My computer went dead halfway through the job, and without a receptacle at the equipment, I had to use my alligator jumpers to snag 120 volts off a single leg of a nearby disconnect for a mini split. Each time you change something with these systems, it takes tens of minutes for that change to become apparent in the data. I hope you enjoyed watching this video, and I hope you were able to learn something. I'm here to learn as well, and if you saw anything in this video that could help me improve as a technician, please let me know in the comments.